There's some cool stuff being done now on trying to detect and predict where landslides will happen using remote sensing, using radar remote sensing, where you bounce radio waves off the Earth and try to see where the Earth has moved little tiny amounts in between each scan. That's a neat application.
So to what scale can it see? How much, like we're talking like millimeters?
Yeah, that's the cool thing is you used to only be able to get that level of detail from ground surveys using, survey sticks to get millimeter surface changes. And now you can do it with some very high powered satellite antenna systems, like antennas the size of your house that can actually measure like micro changes in the surface heights. But it's cool. They can start to predict where these faults are going to happen and where the land's going to slide before it happens.
Cool.
Yeah. Wait here, I'm going to pull up my presentation. Don't worry, it's mostly pictures. Cool. And I want you guys to stop me when I go too deep into something that doesn't make any sense. Just tell me, like, what are you talking about? Because I might get into that. So, yeah.
All right.
Cool. So last week we covered a lot. Like I covered a huge range of topics of things that, I do and I'm interested in, and hopefully you guys found interesting too. So before we get into today's session on remote sensing specifically, was there anything, any follow-up questions from last week where you guys had some burning questions about anything I showed or talked about you wanted to chat about?
Anyone? I guess one thing that I noticed, just all the, other than the remote sensing part of it, but aside from that was the all the crazy creatures. You sent me that other slide share of the places that you were and the fauna and flora that you came across. Mm-hmm. Just incredible, just the diversity of different things you've got to see in your travels.
Yeah, some of those pictures I took, those were all my photos. Some of those places have never been glaciated. So they're little tiny pockets of the Earth that has never had a glacier since the time of the dinosaurs covering it. And so there's some really unique plant species and insect diversity of things that are not found anywhere else in the world. It's like you travel back in time millions of years when you get into these little valleys of ancient mountain ranges in the middle of Brazil that have been there since the time of the dinosaurs.
Yeah, crazy. And then just another thing that kind of just how big picture it's. I mean, some of the stuff you're doing is small scale, but it's small scale to get a big picture.
Yeah.
Like, right? Like, you're putting all the little sensors on the tops of different things to check out, like the humidity or I guess the carbon dioxide to see the breathing Earth. But in the end, it's to give you a bigger picture of the overall, what's going on overall, right?
Yeah, that'll be a common theme in what we talk about today is scales, spatial scales. I'm trying to figure out how do we measure something that we're interested in that happens on a really small scale. It could be a cellular process. How do we measure that in a way that we can map it effectively and accurately over a whole region, an entire province, a whole planet? That's a science in itself. It's called scaling up observations. So that's a big challenge in remote sensing, and it's something that is actually really, really difficult to do well, but it's come a long way recently. That's actually what I specialize. That's one of the ways I actually make money professionally is helping companies figure out how to do that, how to take their ground measurements and scale it out to an entire landscape accurately. Do you guys want to jump into it, or you want to keep spitballing?
I think we're ready. Oh,
cool.
Oh, wait. Here's Brent. Here's Brent. I was telling you about Brent, I was telling him about you were talking about what you heard on CBC. Oh.
They were just talking about, they referenced remote sensing, so I thought it was really cool, seeing as we've been talking about that a little bit. But they are talking about a landslide that happened in India. And so it was a UBC professor from here that's studying this landslide and trying to look at some of that data. But then she referenced some of the stuff around here where they're looking at landslides and how much they've moved, or monitoring that and using remote sensing to do that kind of stuff. So it was pretty cool.
Yeah.
That's cool.
Yeah.
Yeah, it all of the research around stuff like landslides used to be very after the fact, very responsive. You know, something happens and then we try to find some imagery or remote sensing data that can capture that event, ideally with data before and after, and then we try to compare the two and figure out what changes happened. And that's the classical kind of approach to remote sensing analysis. You get this kind of before and after data set, try to find the difference, and then create a set of information that you can then use to improve the situation, predict it happening again. Now it's moving towards near real-time use of that information. It used to be like, it could take a few weeks for somebody to do that kind of analysis on that data to figure out, here's the extent of the slide and here's the number of houses it covered and the damage it inflicted. And now we're at a point where we can actually get the data from the satellites within minutes of the imagery being collected, and have supercomputers that are trained on how to analyze it and tell us exactly, within the hour, the answers to those questions, which is pretty cool to see happening. It's very much the remote sensing world today, the stuff that's available for the average everyday scientist or citizen scientist or computer scientist, is the type of tools that were available to militaries and defense agencies like 20 years ago.
Right.
So a lot of opportunities now, just because the costs have come down too, and the computing power has gone up.
Huh.
Yeah. So that actually touches on a lot of these things here. Like, what is remote sensing?
Yeah.
Well, it's all of these things together. It's a combination of the sensors you're using, like drones or satellites, the data they collect, whether that's imagery or some other type of spatial information. It's the software that we use to process it. It's the analyst that tries to figure out, how do I get the information about the questions I have about a location using the software and the data from these sensors. And that's, people have entire careers as a remote sensing or geospatial analyst. So it's a whole suite of things that remote sensing kind of touches on, all related in some way or the other. And some people specialize in some of these things. I ran a company just on using drones for remote sensing. I did my PhD in satellite remote sensing. So I've got a good spread of experience in different types of technologies for remote sensing. But some people are their job is literally just to take an image and try to figure out, where's all the features in there? Where's all the roads? Let me map out all the cars. Like, that alone is a job. So there's different specific roles for each of these. We're going to take a very general approach to it today, and actually just look at the concepts and the sciences and how remote sensing works. How do we do this stuff? What are the principles we use? So the textbook definition here of remote sensing is a technique used to gather information about an object that does not require you to touch it or make physical contact with it. So that's the most general way of thinking about it. When we then talk about what the science aspect of it, the scientific process, is actually exploring and experimenting the interaction between light and physical matter. It's how light waves, come together, and what happens to a light wave when it hits an object, and how can we use the information that comes off of that object to understand properties of it. And there's important principles that you have to follow to make sure that if I'm the person trying to interpret what the light reflection is telling me off of an object, that if somebody else wanted to use the same technique, to understand about another object using the same methodology, they'll get the same information. Basically, standardizing something is what makes it a scientific approach, and making sure that, just because you use a different type of sensor and you want to measure something about an object over there, you're not going to get a completely different answer. You have to make sure that the information is consistent so that it's not subjective interpretation.
Right.
So
It falls in with with science, right? It has to be,
Yeah.
you have to be able to get the same results if you test it under the same conditions.
that's right. Consistency, transparency, following the proper procedures to make sure that anybody can do it and get the same answer to a question. That's key. So the most simplest way to think of what we actually do to get information about objects far away from you using light waves is to think about when light beams hit something and they bounce back off it. The pattern that the light sends back our way tells us a lot about the object. So what do you guys, think of when you see this image? What kind of object is creating this pattern?
Yeah, getting water. We're getting a resounding water.
Right. That's kind of a no-brainer for most of us, because we've seen how light reflects off an object. Now, do you think if the water was perfectly still, no movement at all, perfectly flat, it would give us maybe a different reflection?
I'm hearing absolutely. I'm hearing, I don't know.
Yeah.
You got-
I mean,
yeah.
that's exactly right. If we had a really choppy, wavy surface, that image of the light coming off it would look very different. And it would be moving very differently too if we were to be looking at a video of it. And our brain can intuitively kind of figure out, if we were only looking at the light coming off of it, we could understand something about the water surface. And in this case, it would be whether it's really, really choppy, if it's really, really still. So that's kind of in the most basic example I can give you, the kind of concept we're using when we're taking light reflecting off of things and trying to use the signal of the light information to understand things we want to know about that object. It's kind of a cheat. Like, if there's something that you can't physically get access to, let's say you want to explore Mars. Well, we can't easily get to Mars, but we can look at how light bounces off the planet and we can get information about it. We know that because we see the planet as red, there's likely something different about the surface of the planet and what it's made of compared to the moon that makes it look a little bit different. And that's a pretty easy way to think about what we're doing with remote sensing. So there's a lot of pieces that go into how we actually measure what happens to light when it hits an object. It's either absorbed, it's either reflected, or it's either transmitted right through it. And the structure of that surface also controls it. If you were to take a flashlight and point it at a mirror, and you take an angle and point it at the mirror, and you'll see the light bounce off and hit the wall over there. You can imagine that if the mirror had some dirt on it or some smudges, you would be able to see those smudges or the dirt in the reflection on the wall, right? Same idea if the mirror surface was really rough and it wasn't smooth at all. Same idea as with the water. You would get a different reflection pattern coming off of it, and that tells you something about the object without having to actually physically touch or feel it.
That new Mars rover that's going there, that Perseverance, it's the first one that actually has a little drone on it. So they have
Right.
It has a little drone that's going to, after it gets where it needs to go, it's going to be able to send up this little drone and get up into the atmosphere a little bit and cruise around, which would be cool.
That is cool. Yeah, and they have a totally different atmosphere too, right? So trying to develop the physics for that. different gravity, different atmosphere, different resistance.
Yeah, it's way less. I can't remember what it was, but it was yeah, way less atmosphere. So yeah, we got a huge parachute when it's coming in, and then
Cool.
yeah, it's neat. Anyway,
Cool. Well, now that we've defined it, why don't we just throw out some ideas on how we think remote sensing might influence the technology we use, the way we go throughout our day to day. Is there any examples you guys can think of that are likely using remote sensing information?
remote sensing information, yell it out. Nice and loud.
I saw this solar thing. It's like a flower. It opens up and it moves with the sunlight. Is that remote sensing?
In a way, that is using a sensor detecting light energy levels and creating, directional intelligence. So yeah, you could argue that is using a remote sensing concept. Yeah. But it's not something you might be using on a day-to-day. If you can try to think of something that you would use almost every day or, once a week,
What's that?
those are the kind of examples we're trying to target.
Someone says TV remote. It's a sensor.
Yeah, that's a good one.
Nice.
Yeah.
What about like if you're looking at the weather, like where the information for weather comes from? I guess that's kind of.
Weather's a perfect example. Yeah, we get all of our models from satellites and all of our forecasts by looking at the Earth from space and trying to predict which direction things are moving. And yeah, that's something you look at almost every day, isn't it?
Any other ideas? No.
Yeah, so no, those are good day-to-day examples and some other examples that are using light energy to tell us things and help us. But the list is long. I mean, the list is really long. So Google Maps is one that a lot of us will use to navigate. Most of the images you'll see on Google Maps, that satellite imagery, that's all remotely sensed information. We talked about emergency responses with the landslide. So if a big natural disaster happens, very common that first responders or emergency teams will get some remote sensing information, satellite or otherwise, to give them the information they need to respond appropriately. Things like mapping out anything and everything on the landscape. So if you want to do maps of vegetation or like wildlife habitat, or you want to know where certain mineral deposits might be located, anything where you're trying to understand, location information about large areas, remote sensing is there. There's non-mapping applications, things like, well, I guess it's kind of mapping, but we talked about self-driving cars last time. Self-driving cars use little laser scanners to figure out where they are all the time. That's a remote sensing technology. So it's a pretty broad category, but I want to focus a lot on the big picture mapping application uses of remote sensing. So my program that I did my university education in was called Remote Sensing of the Environment. So it's using remote sensing principles to map landscapes and natural resources and look at things like forests and deer populations and water resources. So that's what I'll focus on today, but it's all based on this. So when I say light, and I'm gonna say light 100 times today, I'm not talking about just the light we can see. I'm talking about all of the light in the entire spectrum of electromagnetic radiation. And it's hard for us to think of these different wavelengths of light that we can't see. But the TV remote was a perfect example. The TV remote uses a light beam that we can't see. It's going to be an infrared light that it sends a signal to your TV receiver. We can't see that, but it's still a light wave. And the whole spectrum is quite large, and we break it down by the size of the wavelength of the light. So for those of you that have learned about the electromagnetic spectrum, you'll know that different colors of light, they look different to us because of the different wavelengths. So blue light has a shorter wavelength than red light. And that's absolutely key to understanding how we do remote sensing, because the wavelength of the light, whether it's a very, very short wavelength, like a blue light or a ultraviolet light, or a long wavelength, like a radio wave, like a Wi-Fi signal is a radio wave. It's a bigger wavelength. That wavelength is the entire reason why light interacts with different materials in different ways. So I'll ask you a question here. I'm holding up this object that is blue. What could you guess about the material that this is made of that makes it look blue? Do you think it's reflecting more or less light in different colors for any specific reason?
What do you think? I got it's reflecting blue light at the back.
That's right. So this thing is a very bright blue. So the material that it's made of has little pigments that are in the fabrics, and those pigments absorb all light energy in the visible spectrum from blue to red, except for the blue. The blue stuff just bounces right off it. And that's why our eyes pick it up. And that's a very important concept to remote sensing, is understanding how different materials might absorb different frequencies or different wavelengths or colors of light. And that's really it. If you can understand that concept, if there's one thing I want you guys to understand today, that's it, is that different materials based on their chemical properties interact with light waves in different ways. And we can use that to measure things about them from a distance away.
So any color that you would see, it's that color, all the other colors are being absorbed, and that's the one that's being
Not absorbed.
not absorbed.
Yeah.
Right.
So technically you could say this thing is actually every color but blue in a sense. It absorbs all the other wavelengths of light. It
Right.
doesn't like blue. Blue doesn't interact with the chemical bonds in the pigments. Blue just bounces right off.
Huh.
So that's a key concept.
Is it planned?
I don't know.
This is a
You got some rumbling here. You're blowing some minds here with our colors.
It's really actually, when you get into the science of how light interacts with matter, I mean, that's what got me hooked on remote sensing, was just how they're invisible things, right? Chemical bonds influence that. So if you've got a chemical bond between a hydrogen and an oxygen atom, that energy in that little bond between those atoms is what controls what light gets absorbed and what light gets reflected. And that's how we can measure things like there's water there because it reflects blue light.
Is that planned though?
What's that? Is that
Is it
planned?
planned? Like if someone wants blue fabric, do they intentionally make it so that it reflects blue light? Or they pick that fabric because
Right.
it reflects blue light?
Oh, right. The question is it planned, or is that just the result of doing things, right?
Yeah.
If you're making a fabric, are you just picking it because it's blue? Or are you making it absorb all the other lights or all the other colors? So it,
Yeah.
So blue's an interesting one because it's one of the only pigments that is very, very rare in nature to occur naturally from living things. So it's actually very, very difficult for blue light to be the predominantly reflected light in nature. So the way natural things or living things tend to make themselves look blue is by having a different structure of the actual surface of the object. So if you think of a blue hummingbird's throat, there's little tiny structural changes in the feathers that make the blue light scatter and bounce back. Same with a butterfly, a blue butterfly's wings. It's the structure of the little tiny scales on the wings that reflect blue light. You won't find a pigment, like a chemical, that reflects blue light in nature. They're very, very, very rare, and they're very, very expensive for animals to produce. So there's very few examples of them. But all the other colors in the rainbow, there's lots of naturally occurrent pigments and chemicals and things that that reflect those light wavelengths.
So then when we think about a sunset, which is, your beautiful pink, right? It'd be because the wavelength is longer because the sun's down in the horizon, right? So as it's hitting our atmosphere, its wavelength is longer, so that it's appearing more reddish pink to us. Is that correct?
Yeah, but basically what it comes down to is, and I actually have some figures on this, is that the different wavelengths or the different colors of light that hit our atmosphere, they interact with different things in our atmosphere in different ways. So red light versus blue light, different wavelengths. Red light gets absorbed more than blue light. Blue light kind of hits things and bounces off it and scatters. And so when the sun goes to the horizon, it's got a lot more atmosphere to go through, and the blue light all gets scattered away before it gets to our eyes. That's why you see more red. But
we got a
yeah,
question.
these are good questions and good things to think of.
Stuff are actually blue because it's the light from stuff in the sky that makes them blue.
The question was, Lucy, louder?
I think I read something about this sometime, that the reason why we perceive large amounts of water like oceans as blue is actually because it's being bounced from the sky.
The ocean's perceived as blue because we see bounce from the sky.
Yeah, it's a combination of the light that reaches the water through the atmosphere, being filtered in different wavelengths, and the properties of how light and water interact. So water absorbs, let me make sure I get this the right way. Water absorbs blue light first before red light. I might be the other way around. I'm gonna have to fact check that one.
No,
But
I think you're correct, because I think it's about deep sea creatures, how they have different ways to hide from different, in different zones, they have different light that they try to block out from. And I know that red light gets down deeper than blue light in the ocean, I think.
see, this is where I was getting confused, because deep sea creatures are often red because they don't want to be seen, meaning not a lot of red light gets down. So
Right. Yeah.
red light gets filtered out first, I believe, because of the wavelength of the light. But it's a combination of, yes, how water actually interacts with light and absorbs blue light and red light differently based on the wavelength, and the reflection of the sky, which looks blue because of the way light interacts with different gases in the atmosphere and particles. But the cool thing is that every chemical out there, every atom and every element and every compound, each has its own fingerprint with how light interacts with it. So you can actually tell what the atmosphere of another planet is made of based on what light hits it, gets absorbed, reflected, scattered, and bounced back.
What the heck is the deal with like where just, because I know that there must be some chemical things. They have seas that are like basically pink colored, and they have like, is that just like different algae and things like that actually do change whether the water itself reflects light differently?
Yeah, just different seas, different waters look different, and just kind of wondering if that's just a result of potentially, I guess, abiotic, right? Like you could have silt and sediments, or biotic, I guess plankton, or
Yeah, it's everything. It's the total mix of what's in the water that'll interact differently with the light and make the water look a different color.
cool.
That's why there's so many different shades. So on top of that, it's also the angle and the intensity of the light, right? Because you can have midday sun come down and the water will look darker versus another time of day. So remote sensing is all about, maybe I'll just jump I'll get back to that. But remote sensing is not only about the properties of the material and how it influences the light when it hits it. It's also about it's called the viewing geometry. If I look at an object from one angle versus another angle, the intensity of the light will change. And that's a big important part of the scientific process of remote sensing, is trying to make sure that we're accounting for those differences and that the signature in the light isn't changing simply because of the way we're looking at it, but it's actually changes in the properties of the material. So there's a lot more levels to how we actually standardize remote sensing observations, and that's one of them. Yeah, these are good questions. So I've got another figure up here, and this one's just to show you guys the scale of the wavelengths of different light. So we only see a tiny little sliver of the light spectrum. It's called visible light, and it's just from about 400 nanometer to about 700 nanometers. And it's no coincidence that we see in that range of light, because it's actually the light that our star or the sun puts out in the highest energy. If you were to look across the whole spectrum of light, and the peak energy intensity of what comes off of our star, which is based on its temperature actually, is right there, right in the wavelengths of light that we see. That should get you thinking about, well, what do things look like on other planets where their stars are different temperatures?
Yeah.
That's another discussion we can have at the end maybe, but this picture just shows us kind of the scale of the range of wavelength sizes. So from the smallest, highest energy waves, gamma rays, X-rays, we're talking about things at subatomic levels. These wavelengths are so tiny, they're such high energy. When they interact with matter, crazy things can happen. You know, you don't want to go into an X-ray chamber and just hang out in there, right? Because that energy is so intense, it'll vibrate all of your molecules on your body and cause some damage. But then when we get further down the spectrum, the wavelengths really stretch out. Things that we call radio waves can be several meters to several kilometers long. So long range, like AM radio signals, they can be hundreds of meters long, and they can just travel long distances without being affected by things like trees. And you know, they can travel long distances without distorting the signal. So the way we think about, okay, if I'm trying to measure something in remote sensing, how do I know what wavelength of light to shoot at it or to measure off of it? It's very, very expensive to have a device that can measure in every single wavelength. It's called a spectroradiometer, and they're very delicate instruments, and they're very expensive. And we put some of those in space, but they don't last very long because space is harsh. So we try to pick the wavelength that we want to detect based on the feature properties. So if we want to measure, you know, buildings on the landscape, we're going to use a long wavelength of light, a low energy wavelength, big waves that actually interact with things like the size of buildings. But if we want to measure chemical properties of something, we now have to look at very, very small wavelengths of light. So that's the other concept that I'm hoping to get across to you guys, to know that depending on what we want to measure at a distance, whether it's mountains on the landscape or a number of blades of grass on your lawn, you're going to have to use a different wavelength of light because it's a function of scale. All right, it's two types of remote sensing. Just to totally generalize, there's active, where we're sending a light beam from a source that we create at something and measuring the response. So like a laser ranger, you know, a radio wave that we create, radar and sonar, and you know, that's actively creating the light signal and then measuring the signal back. There's also passive remote sensing, where we're just using an existing energy source of light and measuring how information comes off it. So the obvious source of light in our world is the sun. So most of the type of remote sensing that's done at a planetary scale is passive. We're just passively measuring the light coming off the sun, bouncing off it. So these are two very important distinctions, because there's a lot of things we can't control when we're doing passive remote sensing. We don't control the light energy coming off the sun. It's very difficult to control the viewing geometry or the viewing angles. And those are all important on how we interpret the signal. But active remote sensing, we control the power output of our laser. We control the direction it's pointed and where we put our detectors. So there's a lot more standardization and a lot more reliable information that comes from active remote sensing, but it comes at a cost. We have to create the power to generate that energy signal. So when you put lasers on an airplane, you got to get a big battery pack. You got to bring a lot of energy with you to generate those laser beams. And so there's costs associated with active remote sensing. I talked a little bit about scale, and this is important. If we're trying to measure very, very small objects, like small plants in the understory of a forest, or maybe a beaver dam habitat structure, we're going to want to get very close. Maybe use a drone, get near the surface of the thing. If we're only trying to cover a few small fields, maybe a few small baseball fields in size, use a drone. If you want to measure something at the whole planet scale, get a satellite. The downside is obviously that when you get above the Earth, you have a whole atmosphere in between the sensor and the object you're trying to measure. So you got to do all this fancy math to figure out how the atmosphere, which is always changing, right? The clouds are never in the same place twice. No two clouds are alike. You got to do all this crazy math to figure out exactly how the sky and the atmosphere is affecting that signal. So this is actually what I do the most, is I help companies figure out, what are you trying to measure? Are you trying to count beehives, or are you trying to measure mountain heights? Let's find the right tool for the job. And that's what I specialize in. Last week, I gave you guys kind of an insight to an introduction to what Earth system science is. Well, the large majority of Earth system science is done with satellites, right? It's the best tool for that job. We're looking at the planet from space, and we're doing all these crazy mathematical operations to try to correct the signal coming off the planet, to standardize it so that if our satellite suddenly craps out, we can build another one and put it in place that measures the light the exact same way, and we can continue monitoring without introducing errors into our measurements. So that's the main principles of what is the science in remote sensing, and that covers the majority of it. And let's go back to that idea of different objects reflecting light in different intensities. So this is a graph that shows three things. We got cheese, we got a tomato, we got lettuce. And the lines are the different wavelengths of light that reflect off it as measured by their intensity in the vertical axis, the y-axis there. So I don't know, can you guys see my cursor, my mouse?
Yeah.
Yeah, so if this line here, I actually have no idea which one is A, B, or C. let's pretend A is the lettuce. In the blue wavelengths of light, it's pretty high reflectance, and then you get into the green and it is lower reflectance. Further into the green, you get higher reflectance, and then as you get into the red, the reflectance stays really high. So this is the signature across the wavelengths of light that represents a green leaf of lettuce. And that's a very different signature than something like a tomato or I think that's either a piece of cheese or butter, but just gives you an idea of the concept of different surfaces and different materials give us different, they're called spectral signatures.
So this is part of that fingerprint that you were talking about. Is that
Mhm.
correct?
That's right. So each one has its own fingerprint. The way it's used most often is for vegetation monitoring, because vegetation does something really cool. It actually acts like a mirror, like it's really shiny in invisible near infrared light. So since the 1980s, we've had sensors in space that actually measure the planet's surface reflectance in blue light, in green light, in red light, and near infrared light. And the near infrared light band actually tells us the most about how healthy our planet is. And, you know, that breathing Earth that we saw, trying to actually measure the degree of breathing and vegetation growth, all uses this near infrared light. Because an unhealthy leaf absorbs near infrared light, and a really healthy one with chlorophyll and happy plant pigments reflects that light. So we can actually do some math and just say, you know, how much near infrared light and how much red light is reflected. That's a happy plant. And people use this all the time for mapping crops and monitoring orchards and vineyards and trying to detect problems in the field without having to go and measure every single leaf themselves.
What about, would they use that for like ocean currents? Because I guess like the infrared would detect more heat, right? And the movement of energy. Would that be what that would be as well?
Yeah, when you're talking about heat, you're talking about something that's in actually the far infrared spectrum. And I'll go back 2 or 3 here. This guy. So this is our visible light strip, just this tiny little strip from blue to red. And then you get into this infrared range. Right outside of our visible spectrum is near infrared. And that's, you can actually take your point and shoot camera, even your cell phone, you put a little filter over top of it, and it'll actually start to measure near infrared light. So you can start to look at things like plant health. But when you're talking about heat, it's far infrared, way lower energy, totally different wavelength of light that's down on the spectrum. But that's exactly right. When we're measuring something like an ocean thermal current, we'll use long wave infrared light.
So there's way more to infrared than I think than we realize. So infrared isn't just, you know, when I think of infrared, I think of, you know, those goggles you detect, like think of Predator really. And you know, you can detect the heat coming off of something, but there's more to it than that, I guess.
Yeah, it is a complicated beast when you try to tease apart the whole infrared spectrum, because you're transitioning from visible light, which is relatively high energy light, to very, very low energy light in that range of what we call, I mean, they weren't very creative when they came up with these terms. Ultraviolet, like we get to violet and then, well, let's just call it ultraviolet. We can't see it, it's there. Infrared, they're just, you know, it's just past red. It's just infra, which is Latin for below. It's just below red. And then they cover this whole range. Like if you're looking at red light, it's got a range of maybe 100 nanometers. The range of infrared is about 3,000 nanometers. So near infrared is what we use in things like TV remotes and a lot of plant remote sensing. Then there's mid infrared, and that can actually detect structural changes in things like, if you wanted to map different species of plants, there's a lot of fingerprint spots in the mid infrared. And then when you want to look at things like gases, if you want to find methane gas leaks on a pipeline, or you want to see if your house is leaking any type of carbon-based gases, carbohydrate gases, that's the mid and far infrared. And so, yeah, there's a huge spectrum in the infrared.
Cool.
So what do we do from space? Well, we build instruments that take pictures in all these different wavelengths of light. So we'll snap a picture in the red wavelength, and we'll snap a picture in the orange and the yellow, the blues and the infrared, far infrared. And then we'll even get into something called shortwave infrared. I mean, it just keeps going, and we can start to tease apart different things. And, you know, clouds will scatter light in all of the visible bands, So that's why they look white, is they reflect all of the visible light back. But radar waves go right through them. They don't interact at all with radar waves. So we can actually measure landscapes in radio waves in all weather conditions. We just don't get the same type of resolution because the wavelengths are bigger. So we can only see big features on the landscape. We don't get it's like blurring your eyes and looking at a picture, just a very low resolution version of it. Here's another example of what we use remote sensing for in agriculture. Put these fancy cameras that look at more than just visible light onto a drone, fly it over field, and we can find all sorts of problems with the plants, like pests and diseases or water stress, or, you know, places where the plants are getting outgrown by weeds. This is a really quickly growing field of remote sensing research.
So like stressed plants, like some that might have like some insect attacking them or something, I guess they would have, you'd be looking for, they would have a different signature, and they'd be able to indicate, you know, how the health of the crop.
That's right. So this figure here shows it kind of how that works is like a stressed out leaf starts to reflect more near infrared light. And what happens is when a plant gets stressed, you've seen the leaves wilting, the cellular structure on the inside of the leaf starts to collapse. And just because of that, near infrared light doesn't get absorbed anymore. It gets reflected. Or sorry, other way around. Let me back that up. Scratch that, reverse it. Healthy vegetation will reflect that near infrared light like a mirror. So we get way more of this NIR, near infrared light, reflected off happy, healthy plants. Whereas the sad ones or the dying ones or the stressed ones they're just going to absorb it because of the structure of the plant. So you can start to look at cool things from like chemical composition, structural composition. Getting all that information lets you do things like predict species or predict, you know, what type of crop is it? How much moisture is in the water? You know, how much fertilizer has been used in one part of the field versus the other part of the field, and try to like do micro applications of fertilizers. So there's this whole field of study in precision agriculture. Let's just put fertilizer right where we need it instead of across the whole field. And those decisions are being driven by remote sensing tools on drones now.
Cool. And I guess that would be a result of like nitrification and all that stuff ending up in waterways and those big, huge algae blooms at the heads of major rivers, right? So they want to make sure they're not adding all these excess nutrients onto the landscape because they end up in the waterways.
Yeah, you can detect all that stuff with the right type of sensor from a distance, which is way more efficient than going around sampling every meter for 10 miles. Now, I've got one more concept for you guys because we're coming up on our time. And it's this idea of making these false color images. Has anyone ever heard of a false color image?
False color image.
Probably not.
Have you? No, never have.
It's a similar idea to taking a photo into an app and putting a filter on it to change the way that the different pixels represent different colors. But what we're doing is actually taking an image that has many different pictures and different wavelengths of light. So your normal standard picture is called a true color picture. We've got a red image, a blue image, and a green image. And we smash them together to make something that looks like how our eyes see things. It's called true color. Almost every photo you've ever seen is going to be in true color because it's how our brain wants to see it. When you change one of those channels for a different wavelength of light, we can start to see things that our eyes wouldn't normally see. It's like putting on goggles that see in different spectrums of light. And suddenly you can see really distinct features that you couldn't see before. It's almost like having a superpower. Is this image on the left is just using red light, green light, and blue light. But if I decided to change the red light image for a near infrared light image, it would look like the image on the right. And now suddenly we can see all these bright red things that didn't really stand out in that first image. And what those are crops. So now we can start to see things with a lot more clarity, where the crops are, where the water is, and where the grassland is, and where the wetlands are. And this is how we do ecological mapping and environmental mapping using remote sensing, is we start to use those other wavelengths of light that we can't normally see that interact with different things on the landscape and different ecosystems in different ways. And they give us these really pretty maps that help us measure things better.
So you can kind of use it to select for particular attributes or things that you're looking for? Is that?
That's right. If you understand the principles of how light interacts with different materials and different surface types, these principles of remote sensing, you can then say, well, if I want to measure water, well, I'm going to use red light or near infrared light instead.
Huh. Cool.
Yeah. So here's an example of a false color image of the Earth. And this image on the right is actually using some type of shortwave infrared light, somewhere between the red light and the heat that we talked about. And the clouds show up in a different color, in this case, blue. So remote sensing is a bit of a science and it's a bit of an art. You get to get creative with colors and try to make different things you're interested in measuring and monitoring pop out of the picture to be able to see them more clearly. Here's a false color image of the moon. And if I told you that the orange color represented a specific type of mineral in the moon dust, which image would you choose to look at if you're trying to map the mineral distribution in moon dust?
Yeah. Cool.
So the moon actually looks like that on the right. We just don't see that with our eyes. We can see them with instruments though. So it gives you a whole new perspective to look at the world. And then of course, when you look back at the Earth, you can start to make really detailed maps of things, you know. It could be very simple. Here's a map of the water and here's a map of the forest. Or it can be really, really detailed. You can start to break down different types of ecosystems. You know, here's a alpine wetland. Here's a Mediterranean fir forest. You can start to get really, really detailed classification. This is called land cover classification. And this is the main thing that remote sensing is used for. So that lets us measure things across the spectrum, from climate change to soil type distributions. And, you know, your imagination can just run wild with it. Excuse me. This is something I work on. I do a lot of tree species mapping. And if we're trying to find a specific type of tree, we'll need to get a specific type of sensor and put it on a drone. Then we go fly the area, do some analysis, and then we've got a count and a location for every single type of a tree on the landscape. So I'm just going to end with a couple more examples.
So just a sec on that last one, Cassidy. If I was looking for Western white pine, you know, they've been susceptible to like a blister rust or a pathogen, and you wanted to find them on a landscape and look for maybe a good seed tree or something. I don't know. Each tree would emit its own signature that you could use to find it.
Yeah, that's right. So it'll have its own spectral fingerprint.
Huh, cool.
There's a lot more to it than that. That's one of the most important pieces of information in species mapping for trees. Yeah. We also use information on like spatial distribution and what's called hyper resolution analytics.
So looking at the signature and also the relative size.
Yep, size and shape.
Size and shape of the canopy and stuff. Yeah.
Yep, location on the landscape, distance to water, all sorts of different spatial inputs help us get a more accurate estimate of species.
Cool.
And then you can go big, like you can look at the entire planet and take these spectral indicators. So this is a map that was developed to look at vegetation distribution and climates on a 1 kilometer by 1 kilometer grid across the whole planet. And then scientists have a relationship between the climate, the vegetation diversity, and animal abundance or diversity. So we can start to do things like map species richness for vertebrates. So big group of animals that you're interested in. Maybe it's monkeys or maybe it's armadillos, and you want to know where to look for them. This is the type of analysis that remote sensing can let you do. So species, ecosystems, resources. This is the potential of using remote sensing data to manage very, very large areas like Canada. Canada's a big place. If we had to focus all of our attention and efforts on just the most at-risk environmental locations, then we might want to make a map like this, which is a map of species in Canada that aren't found anywhere else on the world. So this helps us figure out, if we have a limited amount of time and money to solve some of these environmental problems, where should we start? A map like this helps us target areas that can have the most impact on preserving and conserving species of interest. Yeah, that's what I got.
Cool. Hey. So we'll just just like last time, we'll do a bit of a kind of a circle, and people can kind of share out something that they liked, something that they took away.
Okay.
Get the lights.
And if you guys want to do a full circle after around this idea of stars having different spectrums of light, we'll get there.
That's. Can you see us here, Cassidy?
Yep, I'm gonna stop sharing my screen and get you big.
All right, there we are. Dill's over here.
Hey.
I like how you could you told us that you could see the entire Earth through this remote sensing stuff. That was interesting that you could see the entire Earth through it.
Well, like with the length of the wavelengths, like the radio waves as opposed to the other ones.
Yeah.
All right. Cool.
I liked how you could pick out individual items and kind of hunt for them in the forest to map it. That's amazing.
They're signatures, right? They all. Cool. Sky.
I like when you showed like the moon and all of the colors and stuff. I thought that was cool.
Yeah. Could you hear that, Cassidy?
I heard part of it.
Yeah, she said she just really liked the moon example, how you could see the different kind of colors and stuff.
Yeah, stuff
drive home
that
that
hides
point.
to us.
Yeah. Hello, Victoria.
I thought everything was kind of cool, but I really liked the moon.
Yeah.
And it was shown with all those different colors.
Yeah, really, the moon really gives you an example of the use. I don't know, it kind of drove home that it has different uses, right? Cool.
Yeah, the moon dust is all different. We just don't see it differently in the light waves that we look at.
Lucy?
Light and color being related the way they are is so wild.
So light and color being related the way they are is just so wild.
Yeah, I mean that's the universe we're in. It's just light and matter.
In theory, there are places where you cannot see color because there is none.
Wait, Lucy, quick talk. I gotta translate. So in theory that there's places where there's no light?
No colors.
No colors.
Like on a genuine physical level, there is no visible color to us. That's why.
Yeah, the things that we call color are just parts of the spectrum that the cones in our eyes pick up when they hit it. That's all it is.
Yeah. Huh. Cool.
And there's a reason for that. There's a reason why all living things on this planet use those exact same wavelengths of light for biological activities. And that's one of my favorite topics to discuss if anybody's interested.
Nice. I guess in looking at the variety of different things that species on our planet can see, right? Is interesting. Like the remote sensing of animals, right? Like how do they see the world? Gracely.
Yeah, I like the moon thing. I didn't know that there were so many different substances, I guess, on the moon. It's cool. Everything with that.
Yeah, she also liked the moon and the fact that it has, yeah, that you can see that it's made up of so many different things. Yeah, cool. Brent.
Yeah, the whole time I was thinking about how do you actually get to see an image that you track in a light wave that we can't actually visibly see, because we see such a small one, and you kind of wrapped it up at the end there with the false imagery that we need to take whatever data is coming back and turn it into something that we can see so that we actually get a visual picture. Otherwise, you're just looking at data all the time, right?
Yeah, and like we're visual creatures. We need to be able to see this stuff to understand it. So like, how do we trick our brains into seeing these different wavelengths and stuff?
Yeah.
Yeah, cool. Riley. We got another moon lover. The moon was a big hit. No, that was super interesting. And yeah, back to your question that you asked us. Yeah, thinking about how our eyes see things are the result of the sun and all these different properties of our sun. So what would it be like on a different planet by a different sun with different properties? I guess we would still see the same light is my guess, or the same things with our eyes, but other things that evolve there maybe would see things differently.
We would. We would still see the same wavelengths of light, but there probably would be a different distribution of light if we went to a different solar system. So there's this concept in physics of black body radiation. If you heat something up, its temperature actually dictates or controls the wavelength of light intensity that comes off it. So you take your marshmallow roaster and you stick it in the fire, hold it there long enough, it starts to glow, right? So if you hold it in there for a few seconds, it warms up and you can probably almost touch it, put it near your hand, but it's not glowing yet. But you can feel heat coming off of it. So it's emitting electromagnetic radiation. Technically, it's emitting light. It's a type of far infrared light. That's what we call heat. But as you stick it back in and you heat it up more and more, it gets hotter and hotter, it starts to glow. And what's happened is the temperature of this thing has increased and it's starting to emit radiation or light in a different frequency. It's starting to have more energy, and the more energy, temperature is just energy. It's the best way to think of what temperature is. It's just the amount of energy in a piece of something, whatever it is, whether it's your marshmallow roaster or not. So as it gets hotter, the peak wavelength of energy coming off of it starts to move and shift. As it gets hotter and hotter and hotter, if this is our peak energy, this 300 Kelvin object is slightly warmer than the Earth, but the Earth is on average, I don't know, 280 to 300 Kelvin. It gives off most of its electromagnetic energy at this wavelength. And we can't see that. It's just mostly heat. But as things get hotter, so 400 or 3000 K, 4000 K, we start to shift that peak output. So this guy, this blue line, this is the spectral signature coming off of our sun. This is the intensity of light coming off our sun. And so it's no coincidence that the wavelengths of light that our eyes can see, the same wavelengths of light that plants use for photosynthesis, are the same. It's the most abundant, high energy wavelengths of light hitting our Earth because of the temperature of our sun. And that's it. So on a different star system, you might have most of the light energy in what we call the red wavelengths of light. And so if we went to another planet that had a different temperature star, most of the life that evolves on that planet is likely adapted to a different frequency of light. And so everything will just look red to us, even though to the things living there, it's probably all different colors.
Whoa.
I'll leave you with that because that's a mind messer.
Yeah. So if we think of any planet that's by a star that's cooler than ours, chances are we would just see red there. Is that
Red light,
red light?
infrared light. Yeah.
Oh, well, that's no good. I want to see the colors of the universe, Cassidy.
Find a star with the same temperature and you will.
Huh. Cool.
Or get some cool goggles that can see in other wavelengths.
Yeah, we had a lady from the Royal Astronomical Observatory, or no, who was she? Anyway, she came in with glasses, and we did spectroscopy, and we could see the different wavelengths, or just the different colors that different things emit, which was really cool.
That's same idea. Like I got introduced to spectroscopy in university, and it was in university chemistry. They're like, here's this little device where you can measure the spectral signature of different chemicals. Yeah. I'm like, oh, cool. What am I gonna use this for? Like, what the heck am I ever gonna use this for? This is neat, but I'm not gonna be in a lab measuring stuff like that. Turns out it's extremely useful for lots of things when you do it on a landscape scale.
Yeah, cool. All right. Well, thank you very much. Cheers. Thank you.
Yeah, thanks for your time, guys. All right. I think I'm set for next week too. If something comes up, I'll let you know. Otherwise, I think we'll start to look at making maps.
Making maps. All right. Yeah. Sounds great.
All right.
Thanks very much, Cassidy.
See you guys.
Bye.